Good morning, everyone. It's Dan Sandick speaking from the Institute for Catastrophic Loss Reduction in Toronto. Thanks very much for joining us this morning. This morning we have Dr. Francis Zwiers, who is joining us from Victoria, dark and early. Dr. Francis Zwiers is Director of the Pacific Climate Impacts Consortium, and he was previously Chief of the Canadian Centre for Climate Modelling and Analysis and Director of the Climate Research Division, both at Environment and Climate Change Canada. Today he's going to be talking to us about challenges in understanding and projecting precipitation extremes. So we know it's going to be an excellent talk because Dr. Zwiers is one of the top modeling experts in Canada and in the world. And we know we're going to learn a lot from his presentation. Throughout the presentation, we invite you to ask questions using the question box. If you're having trouble finding that, if you can go up to the top right of your screen to the panel and expand that panel, the question box should pop up. You will be able to ask questions anytime during the webinar, but we'll save all questions until the end of the webinar, and then we'll have a moderated discussion afterwards. If you have any questions about using the question box, I think you could probably use actually you can't do that, but you could email Tracy Waddington if you're having trouble, and we can sort it out for you. Just to let you know, while I have your attention, on November 25th, we'll have John Duong from Halton Region providing a webinar talking about Halton Region's flood mitigation work following the 2014 Burlington flood. So with that, I will pass it over to Dr. Zwiers.
Thanks very much, Dan, and good morning to everybody. Thanks both to Dan and to ICLR as a whole for the invitation, and thanks to all of you for making time to listen to me for a while. I'll try to entertain you for the next hour or so, both scientifically but also visually. So if you find the science a bit boring or maybe simply difficult to understand, then perhaps you can distract yourself by looking at the photos. I'm responsible for almost all of the photos, with one exception. So, and you'll see what that is pretty soon. So I'm going to be talking about precipitation extremes, and the way the talk will be organized, I think about half the time or a little bit more will be discussing things that are quite well established that we know, and then I'll spend about a third of the talk or a bit longer talking about some specific challenges that have to do with how we estimate engineering design values. Now for some reason or other, there we go. I figured out what to do. So here's an outline for the talk. There'll be an introduction, some description of observed trends, some discussion of the causes of those changes, and of course that requires climate models. So I have to say a little bit about how well climate models simulate extremes or don't simulate extremes. At that stage, there'll be an opportunity for you to interact just a little bit by answering a question via a poll that Tracy will put up. And then there'll be a part of the talk that talks about how it is that we could improve engineering design values. Some discussion, and if time permits, then I'll discuss a little bit about projected changes in extremes for the future. Now, I would really like to acknowledge Jubin Jiang and his colleagues at Environment and Climate Change Canada. So he's a fellow whom I collaborate with a lot, and the second part of the talk will really be about work that's in progress that he and I and his colleagues are undertaking. By way of introduction, so all of these photos, almost all of these photos have water in them of some kind or other. They're often from the West Coast, and so often the water that's in liquid form at least is salty. But you can see in almost all of these photos water and maybe in both the gas phase, vapor, and salty phase. So here's the thing that maybe motivates most strongly our concern about precipitation extremes, and this was a photo that I didn't take, but it shows you the state of the Calgary East Village area on June the 25th, 2013, just a little bit after the big flooding event that took place there. And so you can immediately see how how the damage was caused in that very costly event. The urban infrastructure is essentially completely flooded. You don't see any suspended power lines in this urban environment. All of the power and communication distribution is underground, and so you can imagine that all of those electrical lockers and communications lockers are not functioning, and as well as the physical damage to infrastructure. There's the damage to the to these kinds of utilities that we depend upon so heavily. 100,000 people were displaced in that incident, but this is always difficult to say. Only 5 people died. Of course, nobody should have died, but in comparison with a similar scale of event in a developing world environment, the number of deaths is very small, and that indicates something about how well adapted and well prepared our society is for these kinds of events. Nevertheless, it's the estimated size of the loss, total size of the loss, is $5.7 billion USD. That's the number that's reported by Munich Re. Only about a third of that was insured. The remainder falls upon us and upon businesses. It's probably the second costliest disaster event in Canadian history, with the recent Fort McMurray wildfires probably costing more. The Insurance Bureau of Canada is indicating $3.6 billion in insured losses, and so when you add in uninsured losses, that number will become a lot larger. So this sets the context for the flooding, sets the context for our concern about precipitation extremes. What I'm going to do now is say a little bit about observed changes in precipitation and precipitation extremes, and this draws largely on the last IPCC report. And so this panel, this first figure here, shows you changes in mean precipitation on a global scale. So these various curves in the top panel, running from 1900 through to about 2010, show estimated global mean anomalies in annual accumulation. So a large variation would be a positive anomaly of 60 millimeters in a year, 60 millimeters more accumulation than normal globally. A negative anomaly would be, a large negative anomaly would be 30 millimeters less than normal over a year, averaged across the globe. So that's 30 millimeters, that's 3 centimeters of water, a little bit more than an inch, covering the whole face of the globe. That's a lot of water. You can see that there's variation over time in this data set. You could imagine that these estimates for early in the 20th century are a lot more uncertain than estimates later in the 20th century. There are more data sets available later in the 20th century, some of them informed by satellite data. Although the primary source of information here in all of these traces is station data, and you can see that there's a substantial, even late in the 20th century, a substantial level of uncertainty in the, not in the sign of of an anomaly, but in the magnitude of an anomaly. And so that's telling us even at a global scale, we don't know with a huge amount of certainty how much wetter than normal a year was, or how much drier than normal a year would have been. The lower panel shows you trends in the annual accumulation from the Global Precipitation Climatology Center that operates at the U.S. National Center for Atmospheric Research. And what's shown here are trends for 1951 to 2010. And so you see in blue places that have become wetter over that period of time on average. The dark blues, medium to dark blues, represent substantial numbers, 10 to 25 millimeters per decade. And that's contrasted by other places where there have been substantial reductions over time in precipitation, with reductions over time of similar magnitude, particularly in the subtropics. If you look at Western Africa, for example, where there have been very large changes. The changes are not everywhere significant, and I'll be talking about that a little bit in the context of extremes. So where they are significant, the grid box in which they're significant is marked with a plus sign. And you see that there's a lot of structure, and with contrasting areas of increase and decrease. And some of those we can understand actually in terms of human influence on the climate system as a consequence of increased greenhouse gases in the atmosphere, and the effects that has on the distribution of precipitation on the face of the planet. But some of that would also have to be traced back to either observational uncertainty. Precipitation is hard to measure, and you require stations in a lot of places in order to be able to document well how precipitation has changed, or to the influence of circulation. So you can imagine that over Western North America, for example, the amount of precipitation that's received depends a lot upon the state of the Pacific, and whether we're in a Pacific Decadal Oscillation positive period or a Pacific Decadal Oscillation negative phase period, and so on. So that's on a kind of on a global scale. If we go to a much more regional scale, so this time series, it's a kind of complicated diagram, but it tries to tell you something about the history and future of mean precipitation change in British Columbia in wintertime. So this is just a representative kind of plot that could be produced for any region in Canada, and I include it here to show you what some of the issues are when you go down to smaller scales. So the way the diagram is drawn, it attempts to emulate the way in which similar diagrams are drawn in the last IPCC report. And first, on the left-hand side of the figure, what you're seeing in dark green is an estimate of the provincial winter mean precipitation anomaly relative to a mean. So it's expressed in a relative way, and how that varies from year to year. And so the numbers there are, the extreme is at plus 75% in 1901. Other numbers vary between kind of plus 50% and minus 30% or so. Underneath that, there are, and I'll talk about that variability in just a second, and how reliable we might think it is. Underneath that, there are many gray traces, and those gray traces come from climate models that are run over the historical period using historical changes in greenhouse gas forcing, aerosols, natural external forcing from volcanoes, and changes in solar output, and so on. And you see that the climate models simulate a variability that is very similar to the variability that's observed. If you went ahead with and simply naively calculated a trend based on the dark green line, then you'd find that there was a trend, fairly substantial, 18 or so % over that 100 years, but it's not statistically significant because of the large variability. And if you thought about how reliable the estimate is for the provincial mean winter precipitation for any particular year, then you come up with estimates of uncertainty that are represented by those light green bars, and so the message there is that these numbers, even on the scale of a place as large as British Columbia, are very uncertain, and that has to do with the fact that that we have relatively sparse coverage of the province with rain gauges, and so we simply don't know the provincial mean precipitation all that well. What happens to these numbers in the future as they come from climate models is displayed on the right-hand side of the figure in colors, and there are three sets of wiggly curves up and down there in deep blue, light blue, and red, and that represents three different forcing scenarios for the future, where greenhouse gas concentrations increase at different rates, that stabilize in the case of RCP 2.6 at a level that might manage to keep global mean temperatures below a 2 degree C increase relative to pre-industrial, RCP 4.5, which stabilizes towards the end of the 21st century, and RCP 8.5, which represents kind of business as usual. The solid curves there show you the median across the projections across the climate models, and there also you see that on the scale of British Columbia, those projections are relatively uncertain. They're indicating an increase in winter precipitation, but there's lots of background variability, and if you were to look in any one single simulation, you might come to the conclusion that there is not a significant trend. And that's simply because it's a signal-to-noise ratio. There's a lot of natural noise on this scale. And so the message is that it's challenging to understand precipitation changes on a provincial scale, let alone on a much smaller regional scale. So to make a few overall statements about changes in mean precipitation. First, they're uncertain due to the state of the observational data. That continues to be the case, although there's lots of effort globally to attempt to improve that. And part of the challenge is simply that we don't have equal density of rain gauges everywhere in the world. We do have several studies that indicate there has been human influence on the distribution of precipitation over the globe, but at very large scales. And basically what they're looking at there are averages around latitude circles, so-called zonal averages. And then what you see is some characteristic changes that correspond to what you would expect as a consequence of increased greenhouse gases. And those characteristic changes indicate that there's an increase in the deep tropics, some drying in the subtropics, and then increases at higher latitudes, mid and higher latitudes. The fact that we're able to identify this information at these very large scales, this influence at these very large scales, provides some basis at least for thinking there might be discernible evidence of changes in extremes as well, which I'll be coming to. And the reason for thinking that is that to the zeroth order, precipitation variability is proportional to the mean precipitation. So precipitation is one of those things that's measured on a scale that goes from 0 to some very large number. And so if you increase the mean, the smallest amount of precipitation that you would observe in a day or a year remains that you could possibly observe remains 0. The largest amount increases, and so the width of the distribution increases, and so variance increases. And so there is some basis for thinking that there might be discernible changes in extremes. And so that's what I'm coming to now. This is based on a 2013 paper with a young fellow at the University of Adelaide. And what we did in this paper was to study trends in the annual maximum one-day precipitation amounts. So think of the wettest day in 1 year. In the so-called GHCN dataset. So the GHCN dataset is a collection of thousands of precipitation records from thousands of stations all over the world. There, in this data set at the time at which we analyzed it, there were about 8,400 stations scattered across the world that had 30 years or more data. Median length was 53 years, and so that's the data that we extended. We analyzed. A few of those stations had data that extend from 1900 basically through to the end of the data set, but that would be the exception. So at these 8,400 locations, all we did was use this one number per year, the heaviest precipitation event per year, and arranged in time. And then we asked whether or not there was a significant trend upwards or downwards in those extreme amounts. And we asked that question at each individual location, so about 8,400 times. The test was conducted at the 5% significance level. It's a two-sided test, and so what you would expect if there are no, if nothing is going on to make the precipitation record anywhere in the world non-stationary, then you would expect to see 2.5% of locations showing significant negative trends and 2.5% of locations showing significant positive trends. That's the expected false rejection rate, and that's something that's unavoidable when you apply a statistical test at a specified level of significance. So what we saw was 8.5% of stations showing a significant positive trend, increasing intensity of precipitation extremes. So that's the red dot on the left panel, and 2% showing a significant decreasing trends, which is pretty close to 2.5%, and that's the red dot on the right panel. That those bar charts, which are identical on the left and right, show what the expected number of rate of false rejections would be in either the negative or the positive direction. If you had the opportunity to repeat this test on independent samples of 8,400 stations over and over again, so that number 2.5% rejection wouldn't be exact. It would vary from one resampling of the data to the other, and what the distribution of rejection rates, actual rejection rates, would look like is what that blue bar chart looks like. It's centered on about 2.5%. It can't be lower than 0. It has an upper tail that extends to about 6%. And so if you see 8.6%, that's very unusual. And it's not something that you would expect in a stationary data set. If you see 2%, it's fully consistent with what you would expect in the sense of negative trends. And the fact that it's just a little bit less than 2.5%, in fact, suggests that there's something that's tugging the distribution of trends in the opposite direction. Okay, so there's a little bit of smoking gun evidence. If you survey all of the long-term precipitation data that we have access to, daily precipitation data that we have access to, that there might be something that is intensifying precipitation extremes over time. So we dug into this a little bit further, and what we did next was to fit an extreme value distribution at each of those 8,400 locations. And we included one covariate in that fitted extreme value distribution. Basically, we asked whether or not there was a relationship between the intensity of the annual maximum precipitation amount and the global mean temperature in that year. So this figure shows you where, first of all, where all of the stations are located. There are 8,400 dots, or 8,376 dots on this figure, indicating where the stations are. It shows you what some of the challenges are, in that there are there's very uneven data coverage. across the global landmass, and that has to do with both where precipitation is observed and the mandates that the different hydrometeorological services around the world have for exchanging data. Some are not allowed to exchange data freely. Some don't have the resources to do it. In other places, there simply isn't very much data, such as northern Canada, because it's sparsely settled. What we found by interrogating this data is that there's a significant positive relationship between intense precipitation and global mean temperature anomalies at about 10% of stations, which is much more than we expect by accident. And there's a significant negative relationship at 2.2% of stations, which is about what we would expect by accident. That's the dark blue and the infilled blue and the infilled red markers on the map. Those infilled markers are, as a function of the number of stations, occur at roughly equal density everywhere, so that there isn't a particular place where this is happening more frequently than others. When you fit an extreme value distribution, then one of the things that you can do with this with a covariate is that you could specify a various value of the covariate, and so we could specify a global mean temperature anomaly of 1%, and we could ask, well, 1 degree, and we could ask, well, what do these statistical models say that implies for the change in extreme precipitation intensity? And the answer is 7% stronger for a 1 degree warming. And this is just empirical evidence that comes out of the data. But it's a number that has a lot of physical significance, because it's also the number that's predicted by the Clausius-Clapeyron relation, which describes how the saturation vapor pressure for water changes as temperature increases. So essentially, the moisture that's available for the occurrence of an extreme event is increased by about 7% when the temperature is 1 degree warmer, and so that's essentially what we're seeing empirically by looking at this data. So there's a little bit more smoking gun evidence that might be humans that are responsible for the on a global scale, the evidence that we're finding that precipitation extremes are intensifying. There's another message in this figure before I move on that is an important one, and that is that if you choose an arbitrary location, and you could choose London, Ontario, or Victoria, BC, or wherever it is that you're interested in, the chances of finding evidence of a relationship with global mean temperature or of finding evidence of a long-term trend is pretty slim. Kind of like one chance in 10. If you choose an arbitrary station, there's about 1 chance in 10 that you'll find a significant positive trend. And so while at a global scale we have, we're learning that perhaps there is an influence that is driving up precipitation extremes. We're also learning at the same time that this is really tough to detect locally and to say things about in your own backyard. And I'll be coming back to that as we go along in the talk. I think I'll skip over this chart. It shows you something about how that estimated sensitivity of extreme precipitation to warming varies with where you are in the world. It's high on the equator, as you would expect, because that's where there's a lot of moisture convergence and very intense precipitation all the time. It's low off to the edges of the tropics and the subtropics where the deserts are. And that's also expected. That's if you have upward motion in the atmosphere on the equator, then there's a corresponding downward motion in the subtropics. That's what keeps the deserts where they are. And so precipitation is very low in those places, and the sensitivity of extreme precipitation to increases in temperature is also very low in those places. And then in the mid latitudes at 40 or 50 or 60 degrees north, where we live, then the sensitivity is roughly the Clausius-Clapeyron sensitivity of about 7% per degree of warming. So you see that the dashed curve off towards the right-hand side. That shaded area at the bottom tells you something about the uncertainty in that number, and the uncertainty is much greater in the southern hemisphere than it is in the northern hemisphere, because this is a land-based number, and there are very many fewer observing sites in the southern hemisphere than in the northern hemisphere. Okay, so the IPCC assessment of changes in extreme precipitation is that is rather nuanced. So this is from the most recent IPCC report, and it's saying that precipitation frequency has likely increased, the frequency of heavy precipitation has likely increased in more land regions than where it has decreased. So that's consistent with what we observe, what you saw in the figures that I've just shown you, and that the intensity regarding the intensity of heavy precipitation, confidence varies regionally, but it's very likely that it has intensified in North America. So particularly south of the border, there's a very rich precipitation record, and with many stations available, and that record has been well studied. Okay, well, so the Tracy, the poll is coming up now just shortly, so we're going to be saying a little bit about how climate models deal with extreme precipitation. And so I have a question to pose to the members of the audience. And what you're seeing here are 2 precipitation time series for a 2-year period, January 1973 through to the end of December 1974. And it's for a region that's centered on Vancouver, and you're seeing in one trace the average daily amount from 40 stations that are reporting in the Vancouver area. And in another trace, you're seeing the output from a high-resolution climate model. So that particular climate model has a 50-kilometer grid roughly, and so we identified the grid box that was centered on Vancouver, and then we identified all of the stations that were reporting in that grid box. We calculated average precipitation for each day in that grid box, and that's what's plotted in one of the traces. The model output is plotted in the other trace. There is no reason for you to expect the extremes to occur at the same time, because a climate model simulation is a free-running simulation. It's not ingesting observed data continually, so it's not a weather forecast. But so what you need to be looking at is the statistical behavior of the 2 traces, and the question that I'd like to pose in the poll is, which is the observations and which is the climate model output? And if the poll goes up, then you'll have about 30 seconds to quickly answer the question, and then Tracy will hand the control of the screen back to me again. So I'll just be silent while you think about this. Well, you should be brave. You have at least a 50% chance of being correct. Okay, so we have 74% of the audience thinks that the blue curve is the observed curve, and in fact, so I was told I might have to click more than once. There we go. In fact, it's the black curve which is the observed curve. And if you thought it was the blue curve, you probably thought so for good reason. So the blue curve simulates peaks that are substantially higher than the black curve, and you would be wouldn't be out of line to think that climate model wouldn't be able to simulate the magnitude of observed extremes well. So that would be a reason for choosing the blue curve. If you looked at the very small events, then you'll see, so if you look at this period between July and September of 1974, for example, that's a time when it's characteristically dry in Vancouver. The black curve shows very few precipitation events. The blue curve shows quite a few more precipitation events, and it shows quite a few small ones. And so that would be a way of distinguishing climate model from observations, because climate models tend to simulate small amounts of precipitation more often than is observed. It's a kind of ubiquitous so-called drizzle problem. But the point of the exercise is to point out to you that it's not entirely a dumb thing to ask whether or not a climate model can simulate precipitation extremes. They do simulate weather, and on a day-to-day time scale, you might have a little bit of confidence in the precipitation variations that are being simulated in those models. The only way you'd be able to assess that is to try to compare the thing that the climate model simulates, which is precipitation on a grid box scale, on a 50 or 100 kilometer scale, with observations that are processed to try to estimate how much precipitation occurred across a region on a 50 or 100 kilometer scale. So comparing against rain gauges is a very tough thing, because rain gauges are observed precipitation on a different scale than climate models are able to simulate. So we have to try to arrange things so that there is a like-for-like comparison. So there are a couple of points here in the literature, that papers that you could look up if you're interested in some evaluation of CMIP-5 climate models with respect to precipitation extremes. So that's all I'll say about climate models for now. Another way of assessing them is to attempt to determine whether or not you can see human influence in changes in precipitation extremes on large scales. And so in order to talk about this, I need to tell you a little bit about how detection and attribution research is undertaken. And so for that, I actually have to write down a few equations. I apologize for that. They're not particularly complex. It's basically a regression problem, and it typically involves a set of three equations. So first, we think of an observed change. So we could think of observed changes in precipitation extremes, averaged over some large area and representing some period of time. So this y on the left-hand side is a vector of maybe the states of mean precipitation at different times over a broad region. And so we think of those observed changes as possibly being a combination of something that is forced, so deterministic, caused by changes in greenhouse gas concentrations, for example, plus noise, and that noise arises from the natural internal variations that take place in the climate system without any forcing at all. So what we understand to be weather. We might think of the thing that is being forced as being a combination of the response to greenhouse gas forcing, natural, volcanic, and solar forcing, and so on. So you might think that there are several influences, and you'd want to estimate what each of those influences are. And so you use climate models to do that. You force the climate models with changes in greenhouse gas concentrations, for example. And you have many climate models, and so you can average across them. And the thing with the tilde at the top on the left-hand side would be that multi-model average for climate simulations that take changes in greenhouse gas concentrations into account over time, over the 20th century. And you could write down a little model for that, and you could say, well, there's a true forced response that the climate models are trying to simulate in the climate model world, and so that's the X without the tilde. But there's also still some noise left over there as well, and that has to do with model uncertainty and the internal variability that the models represent. And then you have to write down an equation that describes the relationship between the signal that you think is present in the observations and the signals that you think the climate models are trying to simulate. And they might not be exactly the same. And so basically you write down then a little regression equation, and you allow yourself the opportunity to change the magnitude of the climate model simulated signals. And you suppose that the thing that you're observing, the thing that is present in the observations, is a combination of several things due to greenhouse gases, solar forcing, volcanic forcing, land use change, changes in aerosols, and so on. And so that's a statistical formulation formalism that is used in detection and attribution, and the statistical questions are all about the noise epsilon and the scaling factors beta. The problem, the standard formulation assumes that the noise is Gaussian, has a normal distribution, and of course that's a problem if we're dealing with extremes. And so, the literature has described various ways in which you could adapt this formalism to extremes, and there isn't a standard resolved way of doing this yet, but there are at least 4 or 5 different ways that have been used. If you're interested, there was a summer school on extremes that was organized by the World Climate Research Program in 2014, and there are detailed lectures and lecture notes there that you could reference if you like at that URL. So this is these series of maps shows a particular approach where extremes in annual daily precipitation extremes are converted to an index, where an index between 0 and 1, where the index has a value near 0 if it's the smallest annual maximum on record, and in this case the record is 55 years in length, or it has a value near 1 if it's the largest annual maximum on record. And so you have a series of numbers at each location between 0 and 1. You can ask what the trends in those numbers are, and that's what's shown in the upper panel. And so you see that there are increasing trends in the rank of the annual precipitation extreme over much of the globe, over about 2/3 of the globe where dense enough observations are available to do this calculation, the northern hemisphere. And that where there are changes are relatively substantial. The second panel shows you the same information, but now we've done some spatial smoothing. And so now you see these more characteristic patterns of increases and decreases. If you remember the trend maps near the beginning of the talk over North America, this smooth map in these trends in the most intense in the rank of the most intense precipitation amount look quite a lot like the change in the mean precipitation. And remember, I'm making the point that the mean and variance are related to each other, so mean and extremes are somehow related to each other. So there's some structure there, and you might think that that structure has something to do with, in the northern mid-latitudes, has to do with circulation, for example. It's probably not forced by externally by greenhouse gas changes. The third panel shows you what comes out of climate models if you do this analysis for individual climate models, climate simulations, and then average across the climate simulations. And so then the structure goes away, but the magnitude of the change average across space is about right. And what you see is kind of a ubiquitous intensification of precipitation extremes as time goes along as a consequence of human-induced changes in the atmosphere, so increases in greenhouse gas concentrations and aerosols primarily. That's what the all refers to. The bottom panel shows you the results that you obtain if you do the similar analysis using climate models that are forced only with changes in volcanic activity and changes in solar output. And there you see both increases and decreases, and simply scattered noise in space. Basically, there's no response at this large scale. So then when you estimate these scaling factors, either using the annual maximum 1-day extreme or the annual maximum 5-day accumulation, then this is a bit of an abstract diagram, but what it's saying is that in the observations you can find the human-induced signal, but not the naturally forced signal. And in extreme precipitation, then you can find it both in 1-day extremes and 5-day extremes. That's an abstract figure, and so we need to give it an interpretation, a physical interpretation. And so, first of all, what it means for the change in this rank, change in this index, or change in this rank. For an average location, it means that the rank increased by just a modest amount, 4% over this 55-year period, due to anthropogenic forcing. Something has pushed up the likelihood that an intense precipitation falls in the upper half of the probability distribution by a little bit over that period of time, on average across the globe, is what that's saying. Because of the way we did the analysis, you can translate that change in rank into things that are easier to interpret. So you can translate that change in rank into a change to an intensification. So it's telling you that for an basically randomly selected location on the globe, the annual 1-day extreme precipitation amount intensified by about 3.3%. We know how much warming there was over that period, and so that means that there was about 5.2% of increase per degree of warming with a large uncertainty band. So that's entirely consistent with this Clausius-Clapeyron relationship. You can turn it into changes in waiting times. You can ask what the waiting time was, what the waiting time today is for an event that was a 20-year event in the 1950s, and the answer is about 15 years, pardon me. So it's happening more frequently today. That little increase, 4%, is, translates into a relatively large change in frequency for a defined size of extreme event. And you can translate it into a number called the fraction of attributable risk, which basically is telling you how much of the likelihood of such an event today is due to human influence on the climate system, and it's about a quarter, which is not inconsequential. Okay. I have some other comments here that are more technical in nature, and in the interest of time, I'm going to pass over those. I'm going to briefly summarize this part of the talk by talking about the IPCC attribution assessment on extremes, which is given in blue there. And it's quite a nuanced statement. It's saying that there's medium confidence that anthropogenic forcing has contributed to a global scale intensification of heavy precipitation over the second half of the 20th century in land regions. So medium confidence, if you study the IPCC report carefully, it means that they're not willing to lay odds because the evidence isn't quite there yet. But there's smoking gun evidence. Okay, so now I'm going to move on to this question about engineering design values, and so it's maybe something that the audience is actually quite familiar with, and maybe many people in the audience know more about this than I do. But there are two kinds of tools that engineers often use in designing infrastructure. One are these so-called intensity, duration, frequency (IDF) curves that tell you what the return period is for a particular size of precipitation extreme for a particular accumulation period. So it's a collection of curves for different return periods that describe expected intensities as a function of the accumulation period. And on a typical chart, these would range from 5-minute accumulations to 24-hour accumulations. And you can imagine that engineering design would need to take accumulations of over different accumulation periods into account when designing infrastructure such as stormwater handling infrastructure in a subdivision. So you'd want to be able to deal with the risk that results from an intense 10-minute event, for example, and also want to have the capacity to be able to carry away the amount of water that would accumulate over a 24-hour period if you had some system for retaining water within that subdivision. These curves, when they're constructed, they often exploit empirical scaling between extremes on daily accumulation and sub-daily accumulations. So we have hourly or stations that report 5 minutes or every 10 minutes, so on. Those observing stations are much less numerous than stations that record daily amounts, and so if we can find these empirical scaling relationships, and that helps us construct IDF curves for those locations. The other engineering concept that we are working on, but which I won't be talking very much about, is probable maximum precipitation, which is a concept that's used to ensure dam safety. It's used to estimate the maximum water input into a reservoir over a fixed period of time. And the approach to finding this number often involves maximizing a product of the precipitable water, the amount of water that's available to be rained out of an atmospheric column, and precipitation efficiency. So you can imagine circumstance where there's high precipitable water and high precipitation efficiency would result in a very large input into a reservoir. Here's an example of a typical IDF curve that I'm sure many people in the audience would be familiar with. What you see here, so the first thing that the eye is drawn to is that there are a number of sloped lines, and those sloped lines represent the intensity. Each sloped line represents a return period, 2 years, 5 years, 10 years, 25 years, up to 100 years, labeled on the lower right-hand side of the chart. And they describe how intensity varies with accumulation period for a given return period. So to read this, the 100-year 24-hour event this is the so-called London CS station, which is located at the London airport, is about 5 millimeters per hour for a 24-hour period. So that's about 120 millimeters or so accumulated over. That would be an estimate of the 100-year event for that location. The estimated 100-year 5-minute event is an event of an intensity equivalent to something like 320 millimeters per hour. So a very heavy dump, but for a very short period of time. The crosses are the estimated return values that come directly from observations at different accumulations. The lines are estimates of return values that are obtained by attempting to empirically find a scaling relationship between the different accumulations, and you see that that at all of the return periods you have roughly the same scaling relationship, and that's something that that we try to exploit in producing these estimates. You see that there's some deviation from those curves as well, and I'll talk about that a little bit more in a second. just to give you an idea where the station is, there's an overhead shot from Google in the lower left of the London airport. There's a red marker on it. That's where the station is at present, apparently. It's a so-called composite station, and that means that the station has moved from one place to another, and it's actually been, the record has been constructed by patching records from different instruments in different locations together. Which is a relatively common thing. Here are some diagnostics that are provided by Environment Canada for that particular station and that particular extreme analysis of extremes. This is for the 24-hour duration, but they provide these diagnostics for every duration. That's reported on the IDF curve. You see that there's an estimate of a trend. That trend is not significant. That's consistent with what I've been trying to say about how difficult it is to identify trends locally. The line that's drawn there is downwards negative, but it could as easily have been upwards and positive. There's a plot called a QQ plot that compares the fitted distribution with the ranked extreme 24-hour rainfall amounts that are observed at that station, and you see that generally there's a pretty good fit, although the fit overestimates the largest precipitation amounts by a substantial amount. And you also see that in the right-hand plot that shows the return level estimates and their uncertainty. So the Gumbel fit, use of the Gumbel distribution is reasonable in this case, but the fitted distribution seems to have a heavier tail than observed, and that's contrary to the general observation that observed precipitation is mildly heavy-tailed. So precipitation events, when you look at long records in the northern hemisphere, tend to display behavior that has a little bit fatter right-hand tail than you see in the Gumbel distribution. And in this case, that's a possible artifact of using a composite station, so where the records are actually taken in two different places. You don't see this behavior when you look at the diagnostics for the shorter accumulations, by the way. Okay, well, there are many research questions about IDF curves and about providing the engineering community with robust information about precipitation extremes, and I've listed several of them here, and I'll just very briefly go through them. One is, well, how do we account for non-stationarity? There are some solutions that are offered in the community, but they aren't broadly accepted yet, I would say, and uncertainty hasn't really been dealt with appropriately yet. Why are we interested in uncertainty? We have a pretty strong body of evidence indicating that the climate is changing. The evidence that the precipitation climate is changing. It specifically is a little bit weaker, as I've indicated, but it's there, and we can anticipate that that extreme precipitation distributions will change in the future, and so we do need to begin to think about non-stationarity. How do we make IDF curves more robust and more reliable? The curves that I showed you that are used all over Canada are calculated at individual stations, and so estimated return levels and return periods have large uncertainties, and perhaps we can borrow information from nearby locations with similar climates to improve those estimates. Again, there are partial solutions in the community, some of which are used relatively broadly, but which still haven't made their way into standard practice. Do climate models reproduce the observed heuristic scaling relationships that I described between extreme precipitation at different accumulations? If so, then perhaps there's information from climate models that we can use to deal with non-stationarity. So at what space and time scales can we reliably exploit scaling between precipitation and other better understood and simulated variables such as temperature? If we can do that, then perhaps we can nail down the impacts of non-stationarity even better. So will those scaling relationships change in the future? That's a big question. It's not entirely clear that the empirical relationships that we find today would continue to hold in a warmer climate. So specifically, can temperature scaling be used? And I'll be talking about that a little bit more in the subsequent slides. Can we provide a firm statistical footing for the calculation of probable maximum precipitation to enable reliable uncertainty estimation in PMP estimates? So I have a postdoc who's working on that. Others have thought about that as well. An important question for the practitioner community is that how should they design for changing risks, and whose interest should they protect in doing so? And you can imagine that different people have and entities have different interests in risks. If you're the builder and designer of a particular piece of infrastructure, maybe your risk only extends over the period of time when you're contractually required to ensure that the building meets its performance standards, and so that might be a relatively short period of time. And so then your interest is in knowing what current risks are, not what the risks in 1950 were, but what the risks today are. So even then, non-stationarity might be an issue to be taken into account. If you're a user of a building, then questions about the risk that you're exposed to are complex. If you use a building for a long period of time, should your concern be that the accumulated risk that you're exposed to over the period of time that you spend in that building, might be a good part of your lifetime, is no higher than a certain amount, or should you insist that the risk that you're exposed to at any particular time is no higher than a certain threshold? If it's the accumulated risk that you're concerned about, then you might actually be exposed to very high risk at the end of the design lifetime of the building, and if you thought about that, you might not find that acceptable. And so, exactly which return level and which return period is used, and the period and future climate for which that number is appropriate is important in making these kinds of decisions. And I don't think I'm not aware that has been thought about very deeply yet in the practitioner community. But that said, I'm not an engineer. I'm running out of time, so I'll very briefly talk about something called binning scaling. This is an idea that so this represents, first of all, a subject of a current collaboration with Jubin Zhang and others. So it's ongoing work. There's an emerging literature on this, and basically the idea is that if we don't have a long record, then maybe to tell us how the annual maximum precipitation extreme is changing over time, then maybe we can deduce information from shorter records where high frequency observations are available, and use relationships between precipitation and temperature. And so the idea emerged that maybe you could study how precipitation extremes change as a function of temperature. And so what this binning scaling business does is attempts to find a relationship between the high conditional percentiles of hourly precipitation and the conditional on wet day mean dew point temperature. So you select a temperature, maybe it's 7 degrees or 6 degrees, and then you consider all temperatures near 6 degrees, say in the range from 5 to 7. And for temperatures within those ranges, within that range, then you identify all the extreme 1 hour, all the 1 hour precipitation amounts that occurred when those temperatures were occurred. when those temperatures occurred, and then you find the very high percentiles of those precipitation amounts. And so you find very high percentiles of precipitation conditional upon a particular observed temperature. And when that's done, so this is an example from the Netherlands, where they've lumped together data from 5 stations. You find these kinds of scaling relationships that are seen in the right-hand panel. So for the 99.9th percentile of June, July, August hourly precipitation, conditional on temperature, there's a rapid increase as temperature warms until you reach a peak, and then there's a decrease. So this kind of shape is actually quite common when you do this kind of analysis. You see that there are some thin traces on here, and the red ones show scaling at 14% per degree as opposed to 7% per degree, which are the shallower sloped lines. So this has been termed super Clausius-Clapeyron scaling. And this seems to be quite a strong and reliable relationship, at least in this case, and has similar relationships that have been found in other places. And so so part of the thinking then is that, you know, if you were projecting a 1 degree increase in warming, then perhaps you could move along here 1 degree, and that would tell you how much more intense this extreme precipitation would be. Okay. Well, it turns out that there are quite a few problems with this, as we're discovering. So the question is, would this provide a reliable means of projecting changes in subdaily precipitation extremes? And the problems are that, first of all, this seems to contradict what we're seeing in both observed and projected long-term changes in daily extremes. So the first part of the talk, we saw observed changes of about 7% per degree of warming, and where the binning scaling kind of a calculation has been done, we're sometimes finding 14% per degree of warming. Okay. So there's both numbers are coming from the observations, and so we need to understand why there's that difference. The observed relationship between annual maximum hourly extremes and antecedent dew point temperature, if you consider that over the long term, so consider just the annual maximum hourly extreme precipitation, and then ask, well, what was the dew point temperature just before that happened? Then you do see a relationship between those two numbers, and it turns out to be in the range of about 7% per degree, as opposed to 14% per degree that you find from the binning scaling. And if you look at long-term trends in temperature, then you see that there are strong trends, but you don't see the corresponding strong trends in hourly extreme precipitation. So there are a bunch of things that don't fit together very well. And what the crux of the problem is that what binning scaling does is tells you about the behavior of extreme precipitation conditional upon the observed temperature. And so it's telling you how extreme precipitation varies in large part around the annual cycle. As the annual cycle, as you go from the cool part of the year to the warmer part of the year, or from a cooler part of the summer to a warmer part of the summer, there are systematic changes in extremes that you would expect, and they're confounded with other things that are happening. There are also systematic changes in circulation that take place as a consequence of the annual cycle. The annual cycle is very strong forcing, very hard for us to translate changes in conditional extremes into changes in annual extremes. And so I think it's what we're learning is that binning scaling is perhaps not the panacea that we had hoped for. I'm going to move on and just go to the summary, and then maybe I'll get guidance from Dan as to whether or not to continue for a few more minutes or to open the session for questions.
Yeah.
Yeah, go ahead, Dan.
Oh, sorry. So I was just going to say it's getting to be about 10 after 11, so we might move toward the question session after you're done your summary.
Okay. Okay. Very good. So what we're learning in our recent work is that these conditional percentiles through this binning scaling relationship, they're not annual extremes, and the annual extreme does not consistently occur from year to year at the same temperature, and so that makes it hard to use the information from these conditional extremes to say something about how annual extremes are changing. And it's the absolute annual extreme that's really important for understanding what the biggest impacts are and how they're going to change over time. So translating a statement about how a binning curve might change in the future into a statement about how an annual extreme event might change in the future is not a trivial problem, and that's because the occurrence of temperature at a particular place is changing in frequency as well. And so there's both a change in the characteristics of precipitation with temperature and a change in the characteristics of temperature that need to be taken into account at the same time. The conditional percentiles that I talked about at the end reflect the impacts of processes responsible for extreme precipitation. But those processes are likely not the same at, say, 11 degrees as opposed to at 22 degrees. So when it's warm, you might expect that deep convection, so convective processes, thunderstorms, and so on, produce extreme precipitation amounts. When it's cold, here on the West Coast, for example, then you might imagine that it's moisture transport from the subtropics across the Pacific onto the coast that produces the extreme precipitation amounts. So it's a very different process that would occur, that would produce extreme precipitation here at cooler temperatures than at higher temperatures, and that's the same everywhere. And so somehow or other, what we're doing is confounding the impacts of different kinds of processes, and that's leading to really difficulty in interpreting what the binning is telling us. So that's the next point down. What we see by analyzing climate models, where we're able to do the binning scaling approach as well, is it doesn't really help us reduce uncertainty to any great extent. So there isn't a magic bullet, and at the moment the conservative advice that we'd give to practitioners in northern mid-latitudes would still be to use the Clausius-Clapeyron relation, so 7% per degree of warming or a little bit higher when trying to choose a design value for infrastructure that would has a long life that's going to extend into a future and warmer climate. But that's still contingent upon having robust and reliable IDF curves for the present and robust and reliable probability maximum precipitation estimates, and I don't think we have that yet either. So we have lots of work to do. And so maybe I'll stop at that place at this point. If there and take some questions, and if there are no questions and time permits, then I could say a little bit about what the climate models project for the future.
Okay, great. Thanks, Francis. We do have a number of questions online. We have about 15 to 18 minutes, so maybe we'll try to get through a few of them and then see if we have time, because this would be pretty interesting at the end here. So a question from Paul Kovacs. Does evidence that extreme rainfall is more likely to increase with warming than decrease suggest an increased frequency of extreme rainfall events, an increased severity of extreme rainfall events, or both more frequent and severe events?
So it's a good question, and the answer is both. So this leads essentially to the next slide, and so this comes from climate model projections, and it's it shows a projection of how in climate model world a 20-year extreme event, an event that was a 20-year event in the late 20th century, how much more intense that would become in the towards the end of the 21st century under the RCP 4.5 scenario, which is a stabilization scenario. And you see everywhere in the mid-latitudes intensification of the order of 10% or so, 10.9% globally. You see a few places where there's decreases, and those decreases don't occur where we live. They occur in the subtropics, where there's an enhanced amount of dry air that's falling out of the stratosphere. If you I don't have the corresponding figure that turns this into waiting times, but here is a figure that shows global mean changes in projections of the intensity of one-day events and corresponding projections in changes in the waiting time for 20-year events. And you see that under all of the scenarios, the intensity of a fixed return period event increases, and the frequency of a fixed size of event increases as well. So the waiting time for a fixed size of event, an event that was a 20-year event in the late 20th century, under the RCP 8.5 scenario becomes, that waiting time is about 10 years, but with wide variation depending upon the climate model, by about the 2060s, and it becomes something like 6 years, again with wide variation, by near the end of the 21st century.
Okay, thanks. Another question from a participant. I was wondering how measurement error, both systematic and random, is handled in your modeling, that is, error in rain gauge measurement.
So that's an extremely good question, and it's an extremely difficult question. So as a community, we have good approaches for and quite a bit of confidence in temperature readings. So and we have good approaches for making temperature readings homogeneous. What we mean by a record that's homogeneous is a record that's not affected by instrumental changes or changes in observing practices or observing locations, so on. Instrumental error in temperature is generally pretty small relative to the range of variability that's observed. So it's a much more serious problem for precipitation. So we've made less progress on precipitation, on the homogenization of precipitation data, in part because precipitation here at a given location is not so strongly related to precipitation even just 50 kilometers away, whereas temperature at a given location is strongly related to temperature at other locations. So if it's warm in London, it's warm in Toronto as well. If it's raining in London, it might not be raining in Toronto. So it's been a lot harder to make progress on homogenizing precipitation data. So generally, what is done is a basic level of quality control. Some adjustments are made to account for changes in the Canadian data in the AHCCD data set, which is an adjusted data set. There are adjustments made to account for changes in catch efficiency over time that have to do with warming. So that in cold climates, an instrument that sits in a warmer environment has a different catch efficiency than an instrument that sits in a cooler environment. But I don't think much more has been done. Where maybe a little bit less concerned about instrument error for precipitation extremes than we are for small precipitation amounts, since we don't have the losses, evaporative losses that occur when you attempt to record small amounts are less of an issue for large amounts. But then there are other things that we might be concerned about. So gauges that are unattended in places where there are very heavy amounts of precipitation, for example. Those gauges in wintertime could cap over, and you might not be recording anything for some period of time.
Okay, thanks. And another question from Paul Kovacs online here. First, he's complimenting your photos. The photos are wonderful. Is the current uncertainty about trends in precipitation extremes likely to remain in the foreseeable future, or are there any expectations that this uncertainty may narrow meaningfully, and if so, why?
So from an observational perspective, I think this remains difficult. From a climate modeling perspective, a development that we're seeing is more frequent experimentation with convection permitting models. So these are models with very fine scales that are operating at scales of 1, 2, or 4 kilometers, as opposed to regional climate models that typically today would operate at 15 or 25 kilometer resolution. But 15 or 25 kilometer resolution, the processes that produce precipitation and cloud and convection are parameterized. Basically, if you think of it, 25 kilometer grid square, for example, it might have several convective cells operating at a given time, and what the parameterizations are trying to do is to describe the average effect of all of those convective cells on the mean atmospheric state within that grid box. As you go to smaller scales in the models become capable of simulating convection explicitly. They don't do it completely at 2 kilometers or at 1 kilometers, but at those scales, the dynamical cores of the models begin to convect, and in those models, intense precipitation is coming to be ends up being simulated with intensities and with diurnal cycles that are closer to those that are observed at rain gauges. And so that's a positive development, but it's one that will turn into usable information and projections on climate change over a relatively long period of time, because of the very high computing cost of running those kinds of models.
Okay, thanks. And maybe a related question. So I think after your discussion about binning, you made the comment that for engineering design, you might assume a 7% increase in precipitation extremes per 1 degree of warming. So I know PCIC does work with municipalities. Is this typically the advice that you give, and is it well received? So maybe just to unpack that a little bit.
Sure, we work a lot with municipalities. Usually, what they're interested in are high resolution scenarios of future climate, which we produce using statistical downscaling techniques, and we use techniques that attempt to respect and reproduce behavior in the tails as well as in the center of the distribution. The questions are not so often about, at least not for the people that we deal with, are not so often about precipitation extremes per se, but they might be about potential changes in the municipality's water supply, for example. We had a project not so long ago with one of the municipalities in the Vancouver area, Metro Van. They were worried about of course, they're interested in how the snowpack will change in the watershed that provides the city with water. And, similar kind of question for the municipality of Whistler. We also had a project with.
Okay, a question, again, another question from Paul Kovacs. Why are climate scientists more confident in projections of temperature and precipitation relative to other climate measures?
So that's also a complex question. So we're confident. So we can kind of divide the world into two things: the responses that are thermodynamic, that have to do with the direct impacts of warming, and responses that are dynamic, that have to do with circulation change. And so precipitation, so we have much more confidence in the thermodynamic response of the climate system than we do in the dynamic response. So if you ask climate scientists to talk about how the position of storm tracks will change in the future, for example, or how the intensity of storms will change in the future, that's a much tougher question for them than answering questions about how they think the temperature of the land surface at a particular location will change, or temperature extremes at a particular location will change in the future. Precipitation is affected both by the thermodynamic response of the climate system, and so that's the aspect that we have more confidence in. So we can say something about how the water vapor content of the atmosphere changes as the atmosphere warms, for example, and what implications that might have for extreme precipitation. So that's one of the reasons why we're so focused on Clausius-Clapeyron. But there's the other thing that affects precipitation is the transport of moisture from other places, so circulation. And that's something that we can say a lot less about. Also, we're not nearly so confident in our ability to say things about coupled processes, so how the land surface and the atmosphere work together, for example, and exchange moisture one between the other. So over land, precipitation at a given location could have originated as water vapor from a large water body somewhere, but it could also have originated as water vapor that's been evaporated out of the soil, and so or transpired by plants, and so there's a lot of moisture recycling that takes place, and those kinds of coupled processes are still not very well represented or understood.
Okay, great, thanks. Another question here. Can you comment on what changes in precipitation extremes might mean for hydrologic extremes?
Well, that depends on the size of the drainage basin. So a small drainage basin, then there are direct implications, right? So a larger 24-hour dump or 6-hour dump would mean more intense flash flooding. For larger drainage basins, it's not such a, particularly in Canada, it's not such a clear question, because the largest floods on so-called nidal drainage basins occur. So those are drainage basins that are dominated by snow storage, occur during the spring freshet when the snowpack is melting. And so the size of the snowpack, how quickly the snowpack melts, so how quickly does it warm in the spring, and when does it warm in the spring, how much precipitation was accumulated over the winter in the form of snow. So how much frozen water is there in the basin when melting begins in the spring? That kind of thing has a large impact on flooding. The Calgary event is kind of an object lesson in a sense. So it was a very complex situation. It's a relatively small basin that is drained by the Bow River that flows through Calgary. The event had occurred at a time when there was still a lot of snow in the basin. So there was a rain on snow kind of situation that exacerbated the melt rates. Because the basin is relatively high elevation and still snow covered, the land surface was still frozen, and so there was little absorption into the land, and so all of the precipitation input, which was substantial but not hugely extreme, plus the fact that there was still a lot of snow in the basin and with no place to go except downriver, led to this big flooding event in Calgary. So it'd be very hard to pin, to say that it was a change in extreme precipitation events that was responsible. In fact, we undertook an event attribution study. I was part of a group that did that using a regional climate model, and the suggestion was that on a relatively large scale of size of southern Alberta, for example, then you could see that that human influence on the climate system might have increased the likelihood of the amount of precipitation that was received during that period. But if you focus specifically on the Bow River, then again it became impossible to say anything because the variability is so large, and natural variability is so large, and the event wasn't, the precipitation event per se wasn't so extreme that you would say, this was the event of the century.
Right. Okay. Complicated stuff. I think we're going to have to wrap it up here at just after 11:30. Before we wrap it up, I'd invite Dr. Zwiers if you have any last comments.
No, I don't. I thank the audience. I think there was a good audience, and it's a large number of people who stuck it out to the end, as far as I can see. So thanks a lot. Yeah, that's right. We had about 50 attendees. It was very well attended. So thank you very much again for presenting. Certainly lots of food for thought for today. And if it's all right with you, Dr. Zwiers will be posting a video of this on our YouTube site. So you'll be able to access it later. There's a number of questions here that we didn't get to. So I suppose if you're able to track Dr. Zwiers down, you might be able to ask him directly. With that, I'll end and just remind everyone that our next webinar will be on November 25th, and that will be John Duong, who's an engineer at Halton Region, and he'll be talking about how the region of Halton's been responding to flood risk in their jurisdiction following the 2014 Burlington flood. So thanks again, Dr. Zwiers, and with that, the webinar is concluded. Great, thank you. Have a good day.